Okay, good afternoon and welcome to MAE 106. This is discrete probability with probability. My name is Richard Kohar and this is lecture 8. This is more examples using the rules of inference. Hopefully everyone can hear me okay. If so, give say so or thumbs up in the chat. And for some reason, this seems to be simultaneously broadcasting on another one. Excellent. Yes, excellent. It is Good Friday. It is a happy Friday. Just one moment. I don't know what's going on with YouTube. There's a bit of a glitch that's going on. I'm not sure why it's doing two streams and I can't seem to stop it on just a second. I will give them just a different link for them. There's some people that are watching it says MAE 113. So just a moment. Okay. Good to go. Excellent. Hopefully the video is not too choppy. So we're going to do some more examples using the rules of inference. So we had done quite a few of those. So in the textbook, we had covered things like the idempotence, associativity, commutativity, distributivity, De Morgan, identity, domination, as well as we had like the excluded middle, we had the contradiction, and we also had the implication and the double negation. So using these rules. So in today's lecture, it's going to be kind of more like tutorial style. So lots of examples. Okay, so the first example is let's show so again, it's kind of like given the implication P implies Q, show that, let's say that the inverse is logically equivalent to the converse. Okay, so let's translate that into some mathematical notation or some symbolic notation. What this says is that the inverse, given the implication P implies Q, the inverse is P implies not P implies not Q, is logically equivalent to the converse, which is the reverse direction. So Q implies P. So this is kind of the proof for it. So we'll start out on the right-hand side, or sorry, on the left-hand side here. So we'll do not P implies not Q. And we're going to apply the implication rule. So the implication rule is P implies Q is equivalent to not P or Q. So in this case, we're going to apply the rule. It's that the first proposition implying the second is logically equivalent to not the first or the second. So again, let me read that out. I'll say that it's the first proposition or the second proposition. So that's the implication rule. Okay. The next thing that we can do is I see a double negative here, and I'm trying to simplify this too, right? I see that I don't have any negatives. So I'm going to try to simplify this one right here. And we have a negation and a negation with P. So the negative of a negative proposition is itself. So it's just P or not Q. And that's called the double negation. Okay. Now what I'm going to do is I see that I'm going to have to change the order. I have Q implies P. So to get it sort of similar to what I want to apply the implication again, I'm going to use my commutativity rule. So that says that the first proposition or the second proposition is logically equivalent to the second proposition or the first. So I can change the places. This is okay. So not Q or P. So this is the commutativity rule. And lastly, I'm going to apply the implication rule. So now instead of going in this direction, which we had done with this, we're going to go backwards. So it's the first proposition, so not Q, implies the second proposition, which is P. Now again, because I have this negation in front of here, I don't have to put that here as well. It's a common mistake. So again, you would treat this like our not P, so this is the not Q part right here. Here's my Q, which is the P. And basically I've just exchanged the letters. So that's okay. So this is the implication rule. So applying the implication by the double negation, the commutativity, and the implication rule again, what I've shown, so therefore, not P, which is up on the left-hand side here, implies not Q, is logically equivalent to Q implies P, or in other words, that the inverse of an implication is logically equivalent to its converse. On a test, we need to write out which rule we are using during each time of the proof. That's a good question. I would say you don't have to. I usually do because it's trying to communicate what I'm doing on each step. So the whole point of the course is, sure, it's to learn some math, which is good, some problem solving, but also it's important for this section, for the liberal arts section, to be able to express things in words as well. So while it may not be necessarily required, it is helpful, and especially while you're learning it. If you get into a habit, you end up writing it out anyways. Does that answer the question? Is it required? No. Is it useful? Yes. How would a test question look like? Well, a test question could easily look like something like that, which is, we could just give you something like that. Show, using the rules of inference, that the not P implies not Q is logically equivalent to Q implies P. Could you give us examples? Yes. These are examples. These could show up on the test. Okay. You know, we'll kind of exchange these words: prove, show. A proof is a demonstration, so it's the same idea. So you can say that prove. Let's say prove that. Let's say that P implies P or Q is logically equivalent to a tautology. And then usually it'll be like using the rules of inference. And then it would probably be something like no marks given for a truth table. So you have to use them. You have to use the rules of inference. So again, we can start out on the left-hand side. So let's say P implies P or Q. So the first thing that I can do is I need to show it's a tautology. So I will convert this to just ors and negations. I don't really have a lot of rules that handle the implication. So converting it with the implication rule, it's the negation of the first proposition or the second. So that's the implication rule. The next thing I can do is I can move the brackets. let's see. So I'll go here, and this will go here. So just moving the brackets, I get not P or Q. This is just by associativity. If you wanted to be quite strict about the rules that we had exchanged this. So P or not to P. So that's just the commutativity. So I'm just exchanging the order. And we know that that is a tautology. So that is the rule that we called the excluded middle. And I believe we called this last step the domination because when we have a tautology or something of the proposition, it's always going to be true, because the tautology with the or, we need at least just one of the propositions to be true. So this is a tautology, and that is by the domination law. So we have shown that the left-hand side is equivalent to the right-hand side. So therefore, there we go. So everyone's okay with that so far. Then what we should do is, trying it yourself, just pull out some paper. So we'll do this exercise together. So for this exercise, just take 3 to 4 minutes and write this out. It'll be very similar, but we have P and Q implies P is a tautology. So hopefully this has given you enough time. Let's kind of work through this then. So I'll start on the left-hand side. And I will apply my implication rule, so it's the negation of the first proposition, or the second, then some people might be tempted to start to move these parentheses, but we can't really start shifting them. We can't move them yet because I have this negation in front here. So what I will do is distribute that using De Morgan's law. So what this is to distribute this negative, or De Morgan's law, it's the negation of the first proposition, and the and will switch over to an or. And lastly, the negation of the second. Okay. So when we distribute the negation, it's a special case. We call that De Morgan, named after a logician. Okay. What I'm going to do is I'm going to exchange these two propositions. So the first proposition or the second is equivalent to the second or the first. So I can switch that. So I write P or not P or not Q. So this is the commutativity rule. So I can switch that, and I can switch this. Why I'm doing that is because I want to do a tautology. I have an or and an or, and because I have all the same logical connectives here, like the or and the or, it's not an and, I can shift the brackets. So now I can do P or not P or not Q. So this is by associativity. So we know that P or not to P, that's a tautology. And then by domination, because again, I have a tautology or something else, it's always going to be true. So that is the, oops, and I wrote tautology. No. The specific rule that is, it's actually called is the excluded middle. But let me just finish writing this first. There we go. Okay. In the next one, Let's do show that the negation of all of what's going to be inside this bracket here. The negation of P or not P and Q is a contradiction. Okay. So starting on the left-hand side, I'll distribute the negative here. So I'll apply it to the negation of the first proposition, and so it becomes from an or to an and I apply the negation to the second. So it's the negation of the first proposition. It switches from an or to an and then we apply the negation to the second proposition. Okay, so this is De Morgan. We see that we have a double negation here, so we go not P and just P and Q. Now I can shift these parentheses because these are the same. So it's an and, so I can write bracket P and not P. Sorry, not P and P. And Q. This is by the associativity. Hopefully I wrote that correctly. Associative. Did I spell this correctly? Good. If I want to be strictly accurate to what we had in our rules, I'll just write P and not P. So I can exchange the order because that's the commutativity rule. P and not P, that is a contradiction. So how can you be itself and not itself? So that's the contradiction right there. So there's an F and Q. So this is the contradiction rule. And this is also another form of domination, is that for the and to be true, you have to have both of them to be true. But this is always going to be false. So because one of the propositions is always false, this is logically equivalent to it always being false. So I was about to write domain. Domination. There we go. So it is a contradiction. So therefore, just as what we've shown, therefore, P or not P and Q is a contradiction. All right, how about this one? So let's find the negation of the following. If you are from Ontario, our province of Ontario, then you will receive a scholarship. Okay. So what we're going to do is we'll say you are from Ontario. We'll call that P. And then you will receive a scholarship. Let's say that this is Q. So symbolically, if we let P be from Ontario and Q will receive a scholarship, this is P implies Q. Well, to find the negation, what that would mean is that it's the negation of P implies Q. Well, the first thing that we can do is we can convert this to our using the implication rule. So I'm going to say it's the negation of the first proposition or the second. So that's our implication rule. We can then simplify that. We can now distribute this negative, or the negation. So I get not P. The or switches to an and I apply the negation to the second. So this is De Morgan. I can further simplify the double negative, so that's the negative of a proposition is just itself. So this is the double negative. So there's quite a few ways that we could well, these are all equivalent ways of saying the same thing. So if I wanted to translate this back into English, this would say that, well, again, using what our P was, you are from Ontario. And you will not receive a scholarship. So that would be the negation of that implication. Now, just to recall, that if we had the implication, this is logically equivalent to the contrapositive. So that's equivalent to not Q implies not P. So if I wanted to say up here, if you are from Ontario, then you will receive a scholarship. The contrapositive would be if you don't receive a scholarship, then you're not from Ontario. Okay. And while we had shown that with a truth table, this is page 4. While we had shown that this is logically equivalent using a truth table, we can also show it using the rules of inference. Okay. That's the nice thing with proofs, is once that you've done enough of these, they start to kind of be like templates. So very similarly to how we were doing something like this, we were showing that the inverse is logically equivalent to the converse. We saw that our kind of method for going through this was that we converted the implication so that we had the or, we had some sort of double negative, we did a commutative property, then we applied the implication. So we can kind of take that same idea, that same proof, and see how this applies to this one. Why mathematicians are so interested in proofs, or we're not really so interested in the results. Well, sometimes we are. But sometimes it's more interesting to see how somebody did it, so that we can take little nuggets or chunks out of what we've seen in the proof and we can use them in a different setting. There's no point in redoing something that you've already done before. It's already been done. It's a proof. But we are using that kind of ideas and similarities to apply to a different problem. So we've seen something very similar. We can try to do what we did here. So we did an implication. So let's clear out the implication. It's the negation of the first proposition or the second. So there's our implication. Let's, I need to try to get the Q over on the left-hand side of the implication. So I'm going to change that, change the order. So I'm going to go with Q or not P. So there's our commutativity property. Now the next thing is I don't have I want to apply the implication rule, but I don't have a negative in front of this. So I can apply a double negative. So what I'll do is I'll go not Q or not P. So this is the double negative. Put some brackets around it. And so now I can treat this like a proposition there, and I'll treat this as a proposition. So there I have it. I have the negation of the first proposition or the second proposition. And that's logically equivalent to the first proposition, so this is Q, or the second proposition, which in this case is not P. And so there's the implication. So how does this compare to what we had done previously? It's kind of similar. There is our steps. We did an implication. I didn't necessarily do the double negation first. I did a commutativity, then did the double negation, and then did an implication. So you'll see that it's very similar. It's not exactly the same. But that's the whole idea of doing proofs, is that after a while, you start to see patterns and apply those things that we've seen previously from other proofs into a new proof. Okay. Let's do one more example before we sign off for the weekend. Okay, so we're asked to show that the negation of the implication P implies Q implies P is a tautology. So again, starting on the left-hand side, I'll get, it doesn't really matter which implication I'm going to get rid of first. Let's do this one first on the inside of the brackets. So not P or Q implies P. So there's the implication. I can apply it again. So it's the negation of the first proposition or the second. So let's just double check. So I'm applying, so there's 1, 2. then I apply that third one again. So there's just making sure. Well, there was one there, and there's now two. I have a double negation, so I can drop that because it's just by the rule, double negation. We've seen something very similar to this before. See, I have an or and an or. I need to get this P or not P together. So let's change these so that I get P or not P or Q. This is by commutativity. Followed by, I'm going to shift the parentheses because I have the same logical connectives of the ors. So now I have P or not P or Q. And we're almost done. Because P or not to P, that's a tautology. We're starting to see the same kind of steps again. So we have, that's the excluded middle. Because I have the or, the tautology dominates, and I'm done. Okay, thank you everyone for tuning in on this Friday afternoon. Make sure to check out some of the assignment questions. They are available and posted on Moodle. If you have any questions, feel free to send me an email, and keep an eye out for office hours. If you are really stuck, feel free to send me a message, and then we can arrange to have some office hours to discuss any issues you're having. Is there any more questions? All good? Thank you for handling the glitch okay with initially. Okay. Yes, have a great weekend. Enjoy the weekend. Take care, everyone.